In this video, we're continuing on with lesson 2.7 and 2.8, where we started talking about proportions. And so last time we looked at how we solve proportions, what is a proportion, and so today kind of looking at some specific applications with proportions. And so the first one of those are what are called similar figures. Our definition for similar figures are that similar figures have the same shape, but not necessarily the same size. So same shape, not the same size. And so because of that, what is true is that in similar figures, like the ones that are shown below in these triangles, in these similar figures, the measures of corresponding angles are equal, and corresponding side lengths are proportional. And so what that means is this. When we are looking at corresponding like sides here, when we look at corresponding sides in these similar figures, so for example, like side AB, this side right here, side AB, it corresponds with side FG in our other triangle. And so what we know is that we can write again, comparison, a ratio of those two sides. So side AB is going to correspond with side FG in our other triangle. And that's true for the other sets as well. Like, so for example, if we wanted to write another one, side AC right here corresponds with side FH in our other triangle, and so we can write that as well. And just like in our past ratios, if we put the first triangle on top in the first fraction, we need to write the side from that triangle on top in the other one. So we would also say like side AC, it corresponds with or it's compared to side FH in our second triangle. And in similar figures, what we know about all those corresponding sides is they're proportional. So we can write those comparisons, those ratios, and we can make them equal to each other because they are proportional. And so because that's true, we can use that information, we can use those proportions to solve for missing sides. If we're missing a piece of our similar figures, we can find it because we know that they are proportional. So let's look at our first example here. In this, these sets of similar figures that are on the screen, we have triangle ABC, and we know that it's similar to triangle DEF. They're the same shape, but they're not the same size, so proportional. And so because they are proportional, then we can begin to compare some of the sides. And so, for example, we know that side AB compares in our other triangle to side DF, right? Or sorry, side DE. And we know also like that side BC in our other triangle compares to side EF. Like they're in the same place, right? AB and DE are in the same place. BC and EF are in the same place, like they are in the same location. They're corresponding on our two triangles. And because of that, we know that these two ratios, they're equal. They create a proportion. So now we can fill in some of those values. Like we know the value of side AB, it's 10. We know the value of side BC, it's 16. We know the value of side EF, it's 12. What we don't know, or what we're missing in this figure, is side DE, this side right here, side DE. We don't know what it is, and so just like anything else that we don't know, our unknown we rewrite as a variable, so I'll just go ahead and fill in X there. And just like we talked about before, 3 steps to solving proportion. First step is we're going to cross multiply, so we've got 10 times 12, which is 120. We've got 16 times X, which is 16X. And what we know is that those two ratios, or those two products, when we cross multiply, are always equal to each other. So 120 is equal to 16x. And then we're solving for the variable. So in this case, we have 16 with the x. We need to get rid of that 16. So how do we get rid of a times 16? We divide by 16. What we do to one side, we do to the other. 16 divided by 16 is 1, or 1x is left, or just x we could write it as. And then again, that value right there, 120 over 16, is our correct solution. we can just simplify. We can't just divide evenly. It doesn't come out as a whole number, so instead we'll just simplify the fraction. So we're going to divide by our greatest common factor, which is 8. And so we get 15 over 2. So our missing value, which was side DE, is 15 over 2, or 7.5 if it asks for it as a decimal. We'll put the 7.5. Awesome. So that's our using proportions to find missing side lengths in similar figures. We know similar figures are proportional, so we can write the proportion and solve for what we're missing. All right, same question here, just a little more word problem, a little bit more. We've got a picture instead of just a couple of triangles, but it's still the same thing. We've got some corresponding sides, so we have the bottom of our triangle, or the distance along the ground, and so that distance is 3 feet compared to 15 feet, so there's our first ratio. And then we have our second ratio, which is going to be our height. And so we have 5 feet right here is the height of our person. We want to know how tall is the height of the building, which it tells us is X feet, and so we don't know that, but we can fill it in. So there's our two ratios that we're comparing, and so we have our proportion set up, and then again we're going to cross multiply. So 3 times X is 3X. 15 times 5 is 75. We know those two products are equal to each other, and then we're going to solve for the variable. So we're going to divide by 3 on both sides. 3 divided by 3 is 1, or 1x, or just x. 75 divided by 3 is 25. And again, make sure as we read, especially through these word problems, what's the question? The question was, how tall is the building? The building is 25 feet tall. Right, there's our missing piece. It's what we didn't know, 25 feet tall for the side of our building. Last example that we're going to look at is this picture of the heart. So we have this giant heart over here that's 14 feet tall. We have the person that's 6 feet tall. And what we want to know is how big should we expect the person's heart to be if the giant heart of 14 feet is for someone who would be, it tells us, 170 feet tall. And so again, we start with kind of our ratio that we know. And so what we know is that if we have this 14 foot heart, that's for a 170 foot tall person. That's the information it gives us. It's the first comparison that we know. So then in our second ratio, our second measurement, if we had a 6 foot tall person, we want to know how tall. It tells us is X. How tall would we expect the heart to be? Our labels stay the same on top and bottom. And then how do we solve proportions? We cross multiply. So 170 times X is 170X. 6 times 14 gives us 84. And then we're getting the variable by itself. And so we're going to divide by 170 since it's 170 times X right now. What we do to one side, we do to the other. 170 divided by 170 gives us 1x, or just x. And then again on this side, there's our answer, right? We already have it in fraction form. It's 84 over 70. We just need to simplify. And so in this case, we can divide them both by 2, our greatest common factor. And so we get that x is equal to 42 over 85. So there's our fraction form for our answer. If we write as a decimal, that comes out to about 0.49. And then once again, make sure we answer the question. So in this case, the question was about what size would you expect the heart of a man who is 6 feet tall to be. And so we would expect that their heart is 0.49 or 42 over 85 feet tall. Like that's how much we expect their heart to be. Excellent. Well, next video we'll continue on with some specific examples of how we can apply proportions, but this is similar figures. We compare the ratio of sides that are in the same location. We call them corresponding. Corresponding sides are written in the same ratio. We write our proportion, we cross multiply, and we solve.